Uh, Good morning, everyone. Welcome to the GISS Sea Level Rise seminar. We're very glad to have Dr. Peter Ditlevsen. He's a professor in physics of ice, climate, and earth in the Niels Bohr Institute at the University of Copenhagen. And he has a background in theoretical physics, and his research focuses on climate research, turbulence, meteorology, complex systems, time series analysis, and statistical physics. And he has published several books on turbulence and climate and has an interest in tipping points in the climate system. And he recently published a paper on a warning of a forthcoming collapse of the Atlantic meridional overturning circulation, which received considerable media attention. And so the topic of his talk today will be related to that, predicting a forthcoming collapse of the AMOC. So welcome, Peter.
Thank you. Thank you very much for having me. And it's now I've been presenting a lot here lately on this, so it's nice to be in a sort of a smaller size colloquium here. So feel free to interrupt anything. But the first thing I'll do is to share my screen, if I'm allowed to do that. There we go. This one here. Good, and I should probably do like that. So I'm heading a large European center on tipping points, and this is what got me all started in this. And tipping points is sort of a buzzword these days, and therefore I thought that I would start out, before talking too much about the AMOC, I will take you on a small tour of the idea of predicting a tipping or bifurcation in the Earth system, and give some motivation for why would we think there would be tipping points in the Earth system at all. So I will take a small detour on this, and the reason I'm saying this is that our best guess for the 21st century climate is what is summarized in the IPCC report, and it's based on climate models. And you all know, and you've all seen these curves 100 times, which are the in the latest report, the SSP, I don't even remember, social economic pathways, which are basically prescriptions for the CMIP Climate Model Intercomparison Project, and in this round was the 6th, and now we're in the 7th round, running models for the near future. And for that, they sort of prescribe these scenarios of future emissions that would give you sort of a business as usual, or a Donald Trump scenario up here, and a sort of maybe unrealistic Greta Thunberg down here, and then the models are run, and these are some 50 models that then give the output that you all know, and this is just pulled out of the IPCC report, and you see this red band here corresponds to these 50 odd models predictions into the future for this red one and for this blue one. And they are sort of pretty much the same. There would be sort of a spaghetti in there of what the different models would do. And somehow, if you think about it, it's sort of a boring result, because if I take the top curve and put it on top of the bottom curve, this looks like a very linear response to the forcing. And that, of course, would tell us that, okay, we can guess more or less what comes out if we know what the emissions are. So that would be the kind of climate predictions that we would know just based on our present knowledge of greenhouse warming and so on. So that is all fine. And here we should keep in mind that what we really do is we more or less tune the models to give a good result for the 20th century, which has a pretty nice linear relationship between the global temperature and then the logarithm to the concentrations as we know it should be. So the question is, if we go back in time, if we can really see that this is such a linear relationship, because back in time, of course, we have had stable CO2 in the past climate, but we've of course had changes in the solar insolation. So what I'm showing here is a proxy record for temperature going back 2,000 years. So this is really an ice core record here. And I've taken the previous plot and just plotted on top of that to say, okay, it seems that apart from some natural variability, which is very large here, but this is because it's just a point. This is just taking from the Greenland ice sheet. So of course it varies much more than the global average, but it seems that has kept sort of a stable level for 2,000 years. Okay. Now we can take that even further back, and here it seems that okay, we can predict climate back in time, because the red line here is not the climate curve. This is the insolation curve. So it looks like what we have here is the climate curve, which is the isotope proxy from Greenland. I will not go into the details of that because this is really a seminar on the AMOC. So I'll do this very quickly. And you see natural variability around the curve, but this here is the solar insolation. So it looks like a nice linear relationship between the insolation and the climate, apart from fluctuations. And this one here is pronounced, that's called the 8.2 K event. That was a cooling 8,200 years ago. But from that, of course, we should expect a linear relationship with the forcing that we get from CO2. Now we can take this one even further back in time, because we know pretty well the solar insolation for at least the past 50 million years. So what I've done here is I've taken extended this red curve back now 120,000 years, right? Which is through the past glacial period. And the little blue thing here is just this one here compressed. And the reason I do that is that we do have data that goes back like that. And now you see, whoops, this is really not a linear response to the red curve. So if we put our eyes right into there, I can help it a little bit like that by looking at the past 60,000 years. The reason I take 60,000 years is that's where the quality of the data is very good, the dating is correct, and so on. So what you do see here is that there's a dramatic shift. Of course, now I'm going back in time, going back into the glacial period here, a dramatic shift in comparison to the solar insolation. So that's not a linear response. What I can put in here is sort of an envelope, a cold envelope here and a warm envelope that sort of linearly follows the insolation. But these are what you all know are the danske events that are extreme climate change within very short periods of time back in glacial climate. This is a completely different climate, and the reason that I'm putting this up now is that this the best of our knowledge, these are events of AMOC collapse and AMOC's restarts back in time. And these are indeed extremely dramatic events. So a jump from the cold state to the warm state, which is actually an onset of the AMOC, a collapse is going the other way here, is a warming of something like 10 degrees in a decade. Compare that to our 1.5 degree in a century. These are climate change that are really, really extreme. And these last for a few thousand years, and then they drop back there again. And then they come in this sort of erratic manner here. And we've had long discussions on if there is some pattern in the occurrence of these. In order to see that and to try to tease out of this time series the dynamics of, in this case, the AMOC, we want to look in details in the statistics. And just to pause it a little bit, so my prediction, of course, for the CMIP models, CMIP 6 models, we have no chance of running them for 60,000 years. That would take, I guess it would take a decade to do that on a supercomputer. But my best guess would be that they would probably be following, if they were started back here, they would be following just the insulation curve that they would be fit with, right? And hopefully next generations of models and so on might be able to give us something like this. So this just tells us sort of the size of the scientific problem we have in understanding these. Okay, so let's see now. I seem not to be able to, oh, there we go. Now let me diverge a little bit into a little bit of mathematics, and not much, but it is necessary for this. So if I can just go back to this, what you can see here are sort of a warm state and a cold state. It's like a two-state system, and off AMOC and on AMOC here. But this is a very erratic signal here, a lot of noise in this signal, right? So we imagine that we have our climate system in two possible states. So an extremely reductionistic way of looking at this would be that, okay, we have, like, I'm a physicist, so I like to think in terms of a potential, that you could be in one potential well or you could be in the other potential well. And you can jump from one to the other given by noise. The description of that is a stochastic differential equation, right? That the pullback to the stable state here is given by a force, which is the gradient of the potential, as usual, but then it's kicked around by a noise, okay? This equation cannot, this is not a nonlinear equation where we have a double well potential like that, which means that we cannot solve this analytically. But what we can do is say, okay, sitting over here in one state, we can do a linear approximation around this state. Linear approximation would put in here the best quadratic potential, which means that the forcing will be linear. And we can write it in this way. Now I write it just as a discrete process, but it doesn't matter if it's continuous or discrete. And I get a process like that when I now write this now as a forcing. And when doing that, I can linearize around this point here. And the forcing at the equilibrium is of course 0. and the gradient is 0. That's the first derivative. And the second derivative of the potential here, the first derivative of the forcing here, gives me a parameter alpha here. So this is just a Taylor expansion. First order of Taylor expansion gives me the linear term. Okay? Now I have the linear term, and this alpha here is important. So let me just repeat that again. That's the first derivative of the forcing. That's the curvature of the potential, right? The steeper the potential, the stronger the force in that, okay? And I end up with an equation like that. So that would be, if I did the continuous process, it would be the Ornstein-Uhlenbeck process, but now I just write it as an AR1 process because I did it discretely. And why do I want to do that? I want to do that because now I can calculate everything. What I can calculate now is I can calculate the variance. The variance is calculated in this very simple way that, well, it's a stationary process. So the square of this one has a mean of 0. I just put x0 to be 0. The mean of the square of the left-hand side is the same as the mean of the square on the right-hand side. And just a very, very simple calculation, you can do it yourself. You get a relationship between the variance, the noise intensity, and this alpha. Okay? This is the well-known fluctuation dissipation theorem. Okay? So now I can just calculate the variance of my process from the two parameters that goes into my equation, which is here, the alpha and the sigma, okay? The other thing I can calculate is the autocorrelation, and that goes even easier because the autocorrelation I just take for the step 1 autocorrelation here, I just step 1 step forward, and I get that from the equation, and I plug it in, and as you probably, most of you know, the autocorrelation is exponential, and what is it in this exponent is again the alpha, okay? So all I need for now is this autocorrelation and this variance, and that is the statistics that tells me a lot about what is going to happen when this tipping point is approached. Let's just get a little bit of intuition out of this. Now, if you look at, as I mentioned before, that the alpha was really the curvature of the potential. So for large alpha, I have a narrow potential. For small alpha, I have a wide potential. And now you can see what happens if I have a process in there. If I have a strong force, I'm pulled back to my equilibrium very quickly. If I have a weak force, I can meander like that. So if I plot my process as a function of time, you can immediately see that for large alpha, I have a small variance, alpha is in the denominator, and I have a long time memory in my process if I have a weak force, right? So if this one becomes flat, I just get a random walk, okay? So this is the meaning of that. Okay, here now comes the important thing. If I have a bifurcation, going to a tipping point as a bifurcation, what happens there is that some control parameter, I'll return to that in a bit here, makes it such that one stable state disappears, I will end up in the other state, right? Regardless of the noise, I'll end up in the other state. But I can also transition the barrier because it's a noisy system by an escape over the barrier here, just kicked by noise, that it randomly went like that. So that's a question. That's these two different types of transition from one state to the other. From one state to the other is called bifurcation induced tipping or B-tipping, and noise-induced tipping or end-tipping. Now, if you now do the linearization here, in this case, from the B-tipping and the end-tipping, and look at what happens when you linearize on where you are. You see, in this case, the B-tipping is exactly where this alpha, this well in your double well potential becomes shallower and shallower, and at some point alpha goes to 0 and you disappear. You meander off here, right? So in this case, what happens is that the alpha goes to 0, changes, but over here nothing happens. Nothing happens. It's just the noise that takes you across. That means that I can distinguish this scenario from that scenario just by looking at these two statistical quantities, the variance and the autocorrelation, which should change. I should have an increase in variance let me just go back here, an increase in variance as alpha goes to 0, and an increase in the autocorrelation. This is called critical slowdown, because I'm slowing down as I approach the tipping point. Okay, let's now I'm going too fast. Let's now look at this in detail for this paleo record. Okay. Sorry, I am now confusing myself in which direction I'm going in. Okay, I'm sorry. Okay. So the critical slowdown, of course, I'm looking at and I will return to that. I'm looking at a statistical quantity that changes with time. As I change the control parameter, that will take me to the bifurcation point. Okay. So what I do need is a window. I plotted a window here. Okay. To tell me what is the variance and the autocorrelation within this window. Okay. And then I started wondering, well, what can I do this? Because I have critical slowdown, which means that as I have an increased autocorrelation, my points within my window becomes more and more correlated, which means that my statistical significance in calculating something gets worse and worse. Okay. But fortunately, I can do it on the computer. So I did these two scenarios on the computer. So this first is the B-tipping situation where I have a tipping here. So what I'm plotting here is what's called the bifurcation diagram. And I'll return to that when we come to the AMOC here. So don't worry if you don't get everything here. So what this shows is one stable state, the other stable state, and the barrier here. So plotted as a function of a control parameter, this will give you a situation where the unstable and the stable points, they meet in a bifurcation point. So this is a bifurcation point and it will jump, right? So what happens here is that it's actually jumping a little bit before, and that's because this barrier is very shallow. So just by noise jumped over here, right? So now I can take my window here, and then I can calculate in that window, I can calculate my variance and my autocorrelation. And you see in this situation, as the theory says, well, it does increase as I'm approaching the tipping point, right? Of course, now here I have tipped, so now the statistics is not stationary anymore here. Now I did exactly the same with the noise tipping here. I just ran it until it by chance jumped, and then I reset my time. So I changed my control parameter linearly in time. So what I really have on this axis is time, which is proportional to my lambda, and it's critical here. Lambda is the critical parameter that tells me that this is the bifurcation point. Okay. Variance is increasing, autocorrelation is increasing. Over here, nothing should happen. because alpha is just a constant over here, the same constant as in that point there, so it just stays flat, and it just stays flat. And this, of course, got me into saying, well, that means that imagine that we are only observing a part of the signal here. I can actually use this as an early warning that if this one here starts increasing, it will warn about something happening over here, namely the bifurcation. Over here, there's nothing that will warn me, okay? Now, let's look then at the data here. Say, okay, can I do exactly the same for this data? Well, I can pick out periods here just prior to the jumps. You see, there's a jump, there's a jump, there's a jump. So now I have a series of situations where I'm flat here, and then it's jumping. Can I, within this purple period, tell that I'm going to jump? Well, I can do exactly the same analysis now on my data as I did on my simulation. When I do that, I get this. And now I just put I have 24 of these. So I just put them together. And I, of course, know when they are jumping. So I just put the jumping in here. I just put the jumping in here at the same time as I did over here. And now I can put it in the same window, and I can calculate my variance and my autocorrelation. And now you can see in the case of the AMOC tipping in the glacial climate here, there are no early warnings. So this one here is comparable to that one. This one here is comparable to that one, and not this one over here, right? So this tells me that, well, back in time, back in glacial time, no change in CO2, no change in whatever fresh water forcing there could be for that. So these were noise induced. Okay, now let me go then to the AMOC here, and now I'm a little scared in an audience of oceanographers, because I'm an amateur oceanographer, so bear over with me on this. So this is, so this graph here shows the kind of tipping elements that we are looking at in our system. But let's just look at the AMOC here. And being very simple-minded here, let's look at this as a basin like that, with a depth here, 1,000, 2,000, 3,000 meters. And when we do a meridional average of that, of course, streamlines have to stay within the basin. So for the 2D flow, we can basically only have cells like this in that flow. So I can describe my flow in this very simple way. There could, of course, be more cells and so on, but let's just assume a cell like that. And you probably all know and better than me that this gives a flow around there. Of course, the intensity of the flow is proportional to the gradient and so on in usual fashion. But let's just split this ocean up in this way, which is, I believe, what Stommel did. And if we simplify even more, we have the northward flow in the top 1,000 meters and the return flow in the bottom here. And for that, we can write the usual Stommel model that you are probably all aware of. And I should probably not spend too much time explaining the Stommel model in this audience. But let me just say simply here, let me just, well, I will anyway, and you can do your email or whatever if this is too trivial here. So basically we have a a southern box and a northern box with a northern temperature and northern salinity, southern temperature, southern salinity, and the change is simply hydraulically given by the water flow from one box to the other box here, which puts in the temperature from the south and of course takes out the temperature from the north in the bottom here, and then whatever heating is happening in that box. Exactly the same for the salinity, but in this case it's just the negative salt put in, which is of course has to do with the fresh water taken out like that. So what you parameterize now is this flow here, right, which depends on the density. So this is a buoyancy-driven flow. That's the whole point, and we can linearize that in the usual way around a mean temperature and a mean salinity, and we get for the density differences this that you're all aware of in the temperature and salinity differences. And for now, let's just, of course, as I put it here with the signs, this has to be a positive quantity. So let's just put this as square of the density. And if I do that, I can write these 4 equations in terms of 2 equations in the temperature and salinity differences, and I get this set of equations. Of course, I'm hiding that these ones are not necessarily, you cannot necessarily do it like that, but let's do it for that. And now the next step is important, which is that we see this as a fast flow system, which means that temperature adjusts much quicker than salinity. And when we do that, we can simply solve for the temperature as a function and put that into the salinity equation, and we end up with this equation for the salinity, right? So this is extremely sort of simple description of the AMOC. So why would I at all bother with this kind of extremely simple description? Well, it contains the essential nonlinear dynamics, and that is maybe a surprise. But let's just look at this in detail here. Let's just look at this in detail. So now let's just plot this function here as a function of s, and you see now here that there are, because of this third order term here, there are 3 states, 2 stable and an unstable state. And if I change lambda here, which is where I cross the second axis here, you can see that we will go through a bifurcation here. That is a saddle node bifurcation, and that's a universal saddle node bifurcation. How can that be universal? Let's just very quickly look at this universal way of having a bifurcation. You imagine now that we have some complicated function, need not be a third order polynomial. It's just a function. Forget about the noise for now. And we want to see when this is 0. When do we cut through this 0 point? So you imagine now that this function f of x comma lambda, so we have a lambda comma x here, but it crosses through through this 0 plane. What does this 0 plane mean? That means that dx is 0. That means that I have a steady state, right? Steady state is when I have a 0 here, disregarding this one here. So wherever the curve I cut through this plane is my bifurcation curve, right? So the bifurcation diagram I showed before was really lying in this plane now here, okay? Now, if I increase lambda such that this surface goes below this plane, goes below this plane, then I have no solutions out here. See, this stable solution and this unstable solution, they merge in the bifurcation point, and nothing exists over here. And I will go, in this case, I will go negative on x in this direction here. So this was the unstable, and this is the stable branch. Oh, I'm sorry. Okay. Now, just from smoothness and so on, I can expand now my function around this point. And you see at exactly around this point, I have that the first derivative with respect to x of f is 0 here. I'm just on the rim of this curve, so 0, and the first derivative with respect to f of lambda is negative. Okay, and when I do that, I can expand this thing here to lowest order in x and lambda, and I get this form. This is called the normal form for a saddle node bifurcation. Being close enough to the bifurcation point, this is how it looks, no matter how complicated this function is. There's some smoothness and so on. So that's the first thing. And I mean, what does this have to do with anything? Let me just go back here. This means that actually, if I look at when this is 0 when x is square root of minus lambda. I'll put it in there. So that means that if I look at this plane, this is exactly a square root function, or it's actually a parabola, but if you look at it in the other direction, it's a square root function. So that is the sign of the normal form of this saddle node bifurcation. Okay, so I went back to look at transitions in real climate models, because of course it's silly to talk to oceanographers about the stormal model here. So, but this is intercomparison. It's a little old study by Ramstorff et al. On models that ran through this usual freshwater hosting hysteresis. These are only ocean-only models, and these are ocean atmosphere models. The bifurcation point is when they drop, okay? But let me then put in the normal form on all of these curves. And if I do that, you see there's a remarkably good fit to all of the curves. Some of them jump before, but that's probably just like a noise-induced tipping, as I alluded to before. But you see here, all of these curves follow very, very perfectly the square root as you get close to the bifurcation point, right? So that's the reason why maybe we can use this also on data from the AMOC. Okay, so here's what I said before, that the steady state, the square root of minus this lambda, so lambda is a negative number in this case. Okay, so now I can linearize again. Now I can just linearize this one as I did in the first case, and when I linearize that, I get this expansion coefficient. So here again, in this case, it is written like the Ornstein-Uhlenbeck process. This is the linear process we had before, and this number here is the alpha from before. That is the important thing, that this is the alpha. And as you see, and the critical value here is lambda equals 0. So you can see alpha goes to 0 at exactly the bifurcation point. Okay. So now I have everything. Again, my autocorrelation is given by this. My variance is given by that. Critical slowdown because alpha could go to 0. Increased variance because alpha is in the denominator. Okay. So just to summarize again, here's the bifurcation curve. Right? Here is lambda 0 being 0. Okay. And if I'm up here, this is really my potential. This is the linear potential. I have a large alpha, and this is a simulation. Looks like this. Small correlation time, small variance. As I approach, this is the purple one here. I get close to the bifurcation point. I get a smaller alpha, larger variation, larger variance, and a longer correlation time. Okay. Now imagine the scenario being that I increase again lambda linearly with time. Imagine lambda being a greenhouse force and giving linear change in freshwater forcing or whatever governs that. And at this time out here, the critical time, I'm passing the critical threshold. That's where I have the bifurcation point. Okay. So now again, maybe it is something I shouldn't spend too much time on. But again, there is a window in which I can detect these two statistical quantities. You have to realize that increased variance and increased autocorrelation are statistical measures. So if I now want to see that I am away from a, say, pre-industrial value, then as I'm not very far away, the change in variance or autocorrelation is very small, then I would need a huge window because I'm looking for a small difference. As I approach the bifurcation point, difference becomes larger and larger, and I get a window in which it's possible to detect it with a given window size. Okay, so phrased differently. So this is, I mean, I know this is a very busy graph here or figure. What I'm saying is I can calculate now, since at each point I can linearize, have the Ornstein-Uhlenbeck process. I know all the statistics. I know with what significance within a given window size I can calculate my quantities. That is, what is the variance of the variance? What is the variance of the autocorrelation? Right? What is the uncertainty in measuring these things? And what I can then do is I can say, okay, what window size? Obviously, the longer the window, the more points I have, the better, the smaller the uncertainty. What window size is required in order to see the difference from the baseline? When can I significantly see the difference from the baseline? And you see, and the baseline is over here in this end of the figure. There I need a window that diverges to very, very large because the difference is very small, and it gets smaller and smaller, the window I need, because I'm approaching the tipping point over here at 0, and there I have an increase in variance, and I have an increase in autocorrelation, and I can get there much quicker. So if I have a window size of 50 years, which is what I'm using, I get this green band where I can actually make an early warning, where I can see the difference. Of course, when I get too close to the tipping point, I'm already in risk of tipping by noise. That's this blue curve here, which means that it's not relevant here. I'm already doomed over here. So this is my window of opportunity. And that gives me full way of calculating how significant would it be when I calculate early warning signals. Okay, this was, I think that's the last very technical figure here. So let's go to the business here now. So first of all, in order to see the pre-industrial level of these early warning signals, I need data that goes back to pre-industrial times. Of course, we only have sort of the rapid array for the past 20 years and so on. So we have to rely on the proxies or the fingerprints. So I'm using the CSAR fingerprint of the subpolar gyre area here, SSTs, as the fingerprint of the AMOC. And from that, you have to subtract global warming and this and that. And I will not go into the details, but extracting from that and extracting the seasonal cycle, this is the signal I have. Okay. So this is my AMOC running from 1870 to 2022. Okay. And that, of course, is the this is probably my Achilles heel. Now, this kind of study was done by Niels Bohr a couple of years back, actually with not only this, but 8 different fingerprints, and he calculated the variance of these different fingerprints and saw an increase in that variance here. And this, of course, tells you that, well, something might be happening. But what we really need to know is if these fingerprints here are significant or not. And there we have sort of a discussion because the sort of general approach is to say, okay, let's just look at one of the curves here. Well, I can see it goes upwards, right? So using sort of a Kendall's tau type of approach, you can see, okay, there's a positive trend. But in my view, that doesn't really tell you much, right? Because you would have to know if, you know, what would be the typical variations. Could this just be by chance, and so on. But now we have the full machinery to do it, okay? And that's what I am going to do now, okay? So this is now my AMOC, okay? So I can now calculate within my 50-year window my variance and my autocorrelation, and you see they are increasing. Okay, I can probably put in lines and say that these are significantly increasing, but significant in comparison to what? Okay. Now I can calculate from my variance, which is here, and my autocorrelation. So these two things are the two things that I calculated from my data here. Now I have two equations in which I have an alpha and in which I have a sigma squared. Okay? That means that now I can calculate my alpha by just inverting this one here. This is what I do here. So this is my alpha, changing in time. And from this one here, I get my sigma squared. And sigma squared is a constant. you see. Okay. So, but now, since I have my alpha and I have my sigma squared, I can calculate everything and I have my window size. Now I can put in a confidence band saying that, say, this is my pre-industrial level of my alpha, and sigma is a constant, so that's not a worry. So if this is my pre-industrial level of alpha, I have all I need for plugging it into the Einstein-Uhlenbeck, telling me what is the uncertainty on the variance calculated within a 50-year window, right? The variance of the variance, the variance of the autocorrelation, and I put in here I don't remember if it's one or two sigma confidence level on these two. And now you can see, at this point in time, right? At this point in time, I know that I'm significantly increasing my variance. So things are happening that is not natural in a sense. I'm significantly away from the natural level. And the reason that I'm stopping here is, of course, that I need these 25 years of data within my 50 years window, because this is the center point. So this point, of course, I can only obtain after 25 years here. So that's why I'm ending this one in 90, whatever, 90, 95 or something like that. Okay. Now I can take this even further, because with alpha being 2 square root of minus lambda, I can calculate my lambda. So now what you see here is a lambda that's going down, pretty much according to the type of scenario that I anticipated. Pre-industrial level, then we start messing up with the AMOC, and we have a linear decrease in this lambda here. Okay. But what does business as usual tell me? Well, I can just extrapolate. That's a linear, that's a line. That is when I cross zero. And that's, of course, what made all the stir, right? That, well, if this thing here continues business as usual, I will end up at zero in 30 years. This is 2057. That's not very far out in the future. So going back, checking back, saying, okay, now I have that. Now I can go back and put in my model on top of everything, right? So what I'm doing here, saying this point, is really finding the vertical asymptote where this one diverges, where alpha goes to zero and this variance increases to infinity. I mean, I get off. So everything fits. So one last independent fit is, okay, how good is this curve here? This is the mean state. How good is it with respect to that AMOC here? Well, let me just take the AMOC and then do a 10-year running mean on that. And that's right on top of the curve. Right? So when I first found this, I thought, well, do I really publish this? So in order to back this up, we did a thorough maximum likelihood statistical analysis, estimating all the parameters. And when doing that, this was basically confirmed. But what we got more was that we also got a full statistics of the uncertainty of when this tipping point here would happen. So this is, now I can put like 95% confidence levels and so on, and you see that that goes all the way up to basically now. So that's of course something that's should not be oversold to the press. But this was sort of the scary analysis, and well, yeah, maybe I should just mention that, but now I think I'm soon out of time. Part of the fingerprinting analysis was how we get the AMOC fingerprint, and what was published was the subpolar minus 1 times global mean. But actually, if you subtract 2 times global mean, you get an even better fingerprint. And this is sort of arbitrary, but so we redid the calculation, subtracting 1, 2, or 3 times, and you see that it changed a little bit, but it doesn't change much in terms of when this is going to happen. So when we publish this, all public, it was just newspapers all over. So we were called up by the first 50 newspapers to give interviews on this, and it's out now in 4,000 news outlets, and it's kind of strange that something like this starts to have its own life, because I cannot really follow. So fortunately, my co-author, my sister, is better at social media than I am, and I understand that we got in a very fine company on social media here. So I don't know if I should be proud or the opposite of that. So but anyway, what would then happen? Now, just a couple of weeks after our paper came out, there was a simulation or a model study by Henk Dijkstra's group, Weston and Dijkstra, on the CESM, the community model run in a hosting experiment. So this is, I think it's a CMIP 5 generation model in which they see the collapse going on, and so these are just model years and so on. And I put in this red curve just to be sure that it did the same. And this is the usual square root curve, and it fits really remarkably well on that. But what you can see here is that the collapse here takes of the order 100 model years, which is a very slow way of collapsing here. But what they do get then after the collapse is something like a cooling in Europe of 10 degrees, 15 degrees in winter, and 5 degrees in summer as the most pronounced result. So this is something we Europeans don't really want to happen. But how quickly it could happen here, I think is also really a matter of debate, because if we look back in glacial times, the estimate from data would be 10 years, right? The estimate here would be 100 years. So my sort of intuition would be that this would take of the order 30 years. So let me just conclude by just jumping back to this one here. So what is, I think, important to realize is that while all the models seems to be capable of having a transition, having a bifurcation of the AMOC, and what you really want is, in this case, to estimate the amount of fresh water needed. But the time of the tipping point, they're all over, right? So it's I think important to realize that though we have that what we've been analyzing here are sort of universal features of a transition, namely the fact that it goes down apparently like this rather simple-minded bifurcation. And I used to, I mean, I've been speaking to journalists and try to think of all kind of analogies and so on. So to me, the analogy is a little bit like a phase transition. All materials, you know, have a solid phase and then it melts into a liquid phase. And close to the phase transition, it all happens in the same way, regardless of details. However, when it happens, if you want to predict that you're about to melt, you can do that when you're close. But if you want to calculate the melting point of iron or lead or water and so on, it depends on the molecular details. And that's a much, much harder problem than the problem that we solved here. So let me end on that note and say thanks for your attention.
Thanks very much, Peter. Do we have any questions, comments? Yes, Dan has a question.
Hi, Peter. Good to see you again. My understanding is that the AMOC, I would say, brings its own salt to the party. And the current is saltier than the other parts of the ocean. So as it slows down, it will have less salt. And therefore, it's sort of its own feedback to have a very sudden shutoff. Is that taken into account in your work, or could there actually be a sort of a faster drop off than maybe the models show and things like that? Or I guess maybe the models take that into account. I'm not sure.
Well, I would say in some sense I'm a very poor oceanographer here, because the model takes nothing into account. It's a data analysis. It just goes out there, looks at what happens, what is the AMOC doing, and from that, predicting what is it going to do. So all of these things, of course, in the ideal world, we would have a model that describes this well, and it could support us in predicting how it's gonna come about. But we are not there.
Okay, thank you.
Any other questions?
Sure, I'll ask a question. So you showed a lot of Greenland ice core records, but insofar as looking at very fine scale past changes in AMOC or sea surface temperatures, there's a lot else out there. So for instance, there's very high resolution records from like the Florida Straits, which can be directly linked to AMOC, or you could even use like IPCC position, which is linked to AMOC, and look at some of the laminated sediments off the coast of South America. Given your current model and these longer time series, does it actually hold up in predicting these sudden shifts in circulation of these other longer term proxy records?
No, I mean it doesn't hold up in terms of the even the Greenland ice cores, because as I showed, and I think that's pretty robust, that these were really not driven by a control parameter, a change in freshwater. It was really driven by random fluctuations that suddenly made this happen. Of course, the waiting time for that was
But
thousands of years.
But you said this was during glacial times. I'm sorry. Let me skip you. During the Holocene.
Oh, during the Holocene, but I don't think we've seen a shutdown during. I don't know if 8.2.
But there's certainly been fluctuations.
Right. Yeah.
And
but
just
and these fluctuations, do we know if they were sort of towards a shutdown or just natural fluctuations due to other things? Of course.
I mean, some people have tried to link the fluctuations to like NAO variability or some other kinds of like, you know, slightly longer decadal scale variability. But so you're saying your model really only will predict a shutdown, I guess.
Yes. That's what I'm saying. But
So
it's also, I think I think we should also. I think it's a very, very valid point.
And there's
very interesting what you're saying, because
still
as I understand. Sorry.
There was still some ice by 8.2 K, but it was very much otherwise a Holocene climate and warmer, certainly in the Europe and North America in the summers than it is today. Like if you're away from the ice sheet, and there are folks who think that there might have been some sort of big perturbation at 4,200 years ago. So it'd be interesting to see if it holds up or if it has any predictive ability out of sample for just the historic period.
Yeah. That would be very interesting to look into that. That I think it's one thing that's sort of I don't have the answer to that, but it somehow bothers me is that we look at different types of variability. I mean, NAO and I mean these shifting patterns and so on. They're not really, to me, sort of. They don't have like a physical mechanism in the same sense as the AMOC. There we can make it more. I mean, climate models would describe this and that. It's more like you see a dominating pattern of variability in there. So it has, in some sense, a different. I mean, in my view, a different nature. And that's also what we have to take into account when extracting different fingerprints of this and that. In what sense things are overlaid or not, and it's so.
Hi, this is Ray Schmidt. I just entered a comment in the chat. The point I'd like to make is that the salinity of the Gulf Stream waters flowing northward in the AMOC will be increasing with the intensification of the water cycle. So even though there'll be more rainfall in the subpolar gyre, which is much greater than any contribution from Iceland, Greenland melting. So it's not clear to me that it's going to be so easy to shut down the AMOC. And the other point I wanted to make is the AMOC is actually driven by internal mixing and not surface fluxes. You can look at our paper from 1999 if you want to think about it that way. We do show bifurcation, but my point is it's not so easy to mess around with the hydrologic cycle as just changing the boundary conditions in the subpolar gyre. Thank you.
But how? I mean, the freshwater. I mean, the hosting experiments. They're forcing from the surface.
They are, but they're artificial.
Yeah. That's true. So you're really challenging the whole idea of the freshwater hysteresis.
Yes, and
that's interesting.
the global water cycle is where I have a lot of expertise, and I'm just saying that the threat has been exaggerated.
Yeah, I'd like to say something about that also. Am I on? Oh, I am. Okay. Yeah, so there's two things come to mind. We all have our own area that we're interested in. I'm interested in the global conveyor belt driven by AMOC. And part of that is the Agulhas leakage, which brings in salt from the Indian Ocean into the Atlantic, some of which feeds into the Gulf Stream, making the Gulf Stream more salty, as Ray has pointed out. And so that's one thing. There's going to be some salt coming in from the other oceans, inter-ocean exchange, that will make the Atlantic salty. Okay, well, you're adding more fresh water to the northern North Atlantic, which is tending to shut things down. But what if the place of the formation of North Atlantic deep water, the sinking limb of AMOC, shifts in latitude and longitude? Maybe it might shift further south or something like that, or further east or west, depending where the salt is. So I'm not so sure, this hosing and adding low salinity fresh water to the higher latitudes is going to shut down AMOC in consideration of salt coming in from the south, increased salt. So I think it's not going to shut down, but the sites of the North Atlantic deep water may shift spatially somehow. That's my comment.
Thanks.
Yeah.
Yeah. So would you just a question to that comment? Does that mean that you would think that those, danske events back in glacial times, they were just shifts of maybe governed by sea ice, or
right?
Yeah.
I think that might be a contributing factor. Yes.
Okay.
You could even have like big shifts for the danske Øster by having a different water provenance for where the water isotopes is coming from. So if you're a Laurentide ice sheet, this is something that like Randy Koester and Jean Jouzel worked on 40 years ago. Like if you just modulate the amount of water coming out of the Pacific to Greenland, you could have huge DO-like cycles.
Yeah, but that's true. But I think nowadays we see more and more, even, most prominently say the Shackleton course from the Iberian. So you simply see in the planktonic foraminifera, you see the Greenland curve, and in the benthic you see the Antarctic curve. So this is definitely not related to isotope differences between Pacific and Laurentide. There's in the chat, there's a difficult question here. If we see in the Paley record, if we also see deterministic chaotic behavior, and that's a good question. We of course see the chaotic behavior that we have in weather and the intensity of storms and all this and that. But deterministic chaos, I would, in my view, that is related to, say, the response of the orbital forcing. And I do think that what we see in the middle Pleistocene transition of going from the 41K year ice ages to the 100K years, quasi 100K years ice ages, that could very well be deterministic chaos in the climate system.
Okay. We also had a comment in the chat from Natasha about the climate models can capture these processes. I don't know if you want to.
Well, I think it relates to what we've been discussing, that the vertical mixing in the climate models. Well, I'm not a defender of climate models. at all. But there are problems there. And I also think that the vertical mixing is really the knob that would tell you how stable the AMOC is there. But obviously, of course, I mean, in principle, you would want to get to some point where you could resolve the real flow, but that's of course far-fetched with any model.
Okay, Marlos has a question.
Yes, thank you. Just one point about, for example, that time series, the reconstruction of the AMOC, right? It has its own problems of definition. I don't know. It depends on a baseline you are trying to figure out. But that was based, for example, on the HADA ASST data, which is known to have lower variance before 1949 because of the data availability and everything. And yeah, there's already a data issue on that, right? And
yeah, that's true. That is true.
yeah, and yeah, also, yeah, I want for you to explain how you calculate that variance, because the variance, if the variance doesn't take into account the autocovariance, right? So the autocovariance itself would increase the variance. So is it the variance before you take that mean state, and how is it for a certain period, or is just one parameter?
Well, the autocorrelation doesn't change the variance in the sense. What it does is it gives you a poor data collection to do that. I mean, in principle, I mean, very simply, you need the independent data points in order to estimate the variance. And if you have a fixed window and you have a longer correlation time, you have fewer points in there to do that. So that influences it. So in that sense, just do it in the very simple regular way. But when with the maximum likelihood calculation that I did not show actually calculated everything in one go. Also the fact that actually it's only quasi-stationary because we're changing the whole system as we go along. And there you have explicit calculations of all the statistical quantities based on the data. So that's
so you have a covariance matrix that take into account both variance and covariance separately.
But I mean, there's only one time series, right? So there's no covariance with other time series, right? There's only this one. So there's only temporal correlations in that one series. But obviously, if you looked at the whole field, I'm not looking at the field in the subpolology. I'm just looking at that one time series.
Yeah, no, but yeah, that time series, right? Because it's a change over time of the variance, right? So I wonder just how you estimate that, right? As you mentioned, it could be a window and everything. So
yeah. So in principle, I mean, the naive thing is just to assume you want a short window in order to be assured that you have a quasi-stationary process, right? If things change, it doesn't really. I mean, it's not really consistent to have a time-changing variance. You have to approximate somehow. I mean, variance is a concept of stationary statistics, right? So you have to have quasi-stationary statistics. That's true. But we do have, we do have control of all the uncertainties that come in there.
Yes. Okay, thank you.
Okay. Any other questions?
Hi, this is Natasha Romanu. Hi, I have a question which actually is to the audience, more like the speaker only. We know that there are measurements of the the transport of fresh water in the Southern Ocean that show that the AMOC is in a bistable condition, right? Are these disputed? Are they not accepted as a good indicator of AMOC stability? If that is the case, then there should be potentially a state where the model the world and the climate models would have to show this bistability. So what other ways do we have of calculating how close we are or how we are approaching the state of the critical threshold, for example, for AMOC tipping, if not statistical methods like the ones that are discussed today? Of course, Peter's presentation focused on the subpolar gyre, not really AMOC. That's not the true AMOC, but it's the subpolar gyre changes. But how else are we? Do we not believe that the AMOC can't be in a bistable regime in modern times?
I think it's a very good question, and I don't have the answer. The only answer I could give is that you know, my modeling friends would tell, right? Yeah, there's a bimodal state, and there's just a paper came out of Hank Dexter's group again, where they and then that's a follow-up on the one I presented. And there they propose another index, which is kind of strange, which has to do with the salt flux at, I think, 42 south. I think that's the tip of Africa and across there. What flows in and out of the Atlantic was also related to a bimodality. They get this hysteresis, so there are two states there. But if we don't believe in the models, I'm not the right one to answer.
Any other comments on that? I guess we're at about 12:30, so we can probably stop there. So, thanks again, Peter.
Okay, yeah. Thanks for having me. Bye.
Okay.